So we're going to start off talking about electric fields. And we've examined the results of electric fields when we've talked about electrostatics. And we've had a particle, another particle, and we found the force that they exert on each other. Whether it's an attraction force between a positive and a negative, or it's a repulsion force between a positive and a positive, or a negative and a negative. I think the easiest way to describe what an electric field is to start off with talking about gravitational fields. Now we're going to start off with Earth. And what this is talking about when we said, if I were to place an object and look at the force that is exerted, it would be as if I were to take me, or any person, and place them somewhere in the region around Earth and find out what the force of gravity is. So if I were to be standing on the surface, and we want to look at the gravitational field, that is, what is the acceleration due to gravity at this spot? But Mr. G, I thought you said the acceleration due to gravity is always 9.8 on Earth. No matter what you do, it's always 9.8. And I don't disagree. When we've done any kind of kinematics or dynamics problems, we've always used 9.8, and we've rounded up to 10 just to make stuff easy for us. And the reason we can do that is because even standing on top of the highest point, Mount Everest, we still see an acceleration due to gravity of right around 9.77 meters per second squared, which can simply be rounded up to 9.8. So there isn't much difference, but there is a difference. And the difference in height really isn't a whole lot in comparison to the distance between the center of the Earth and us in Bettendorf, as opposed to the center of the Earth and somebody standing up on top of Mount Everest. But if we were to look at something like a satellite which finds itself way out here, we would notice the acceleration due to gravity be slightly less because it's much farther away from the Earth. Now on top of that, we can look at which direction does the acceleration due to gravity happen. And it always acts towards the center. Always acts towards the center of our objects. So, downwards, and based off of here, downwards. Now to be more accurate though, these two vectors showing the acceleration due to gravity, if I'm farther away from the Earth, it should actually be much smaller, denoting that it has a smaller acceleration due to gravity. Now, we can convert this back into electric fields. We're going to start off with a negatively charged particle, and we're going to look at which direction this field would act in terms of placing an object around it. Now, when we place an object in here, we place a very, very small positive charge. A small positive charge, something like a proton. If we were to put a single proton in here, what would happen to it? In which direction would it go? Now, since this is a proton and we have a large negative charge, my proton would want to go towards the negatively charged particle, just like it would if you were to have a satellite in the Earth, right? So it would be a small line. Now the closer you are with that small positive charge, the bigger that line would be. So when we look to draw electric field lines, what we do is we imagine that we placed a very, very small positive charge, and we look to see what it will show. Which direction will it move? If I were to put a point here, it's going to act straight towards the center. And same thing here, and here, and here, and going along all the way around. We would see this uniform kind of sun-shaped line. And we want to show the direction that these are all going. So how we're going to show that is by putting a little arrow, right? So all of these arrows are pointing in towards the center. So far it doesn't seem too difficult. And the way we can talk about the strength of an electric field is to say how close the lines are together. Now the strength of the electric field somewhere here, right, in this region, those lines are pretty close together. Now if I took the same box and I move it farther away, I only get one line. And if I drew a whole bunch more lines into here, we would see that this might have something like 3 or 4 or 5, but here I might only get something like 3. So this box farther away, I only have 3 lines involved. I think that might be just out of the screen, but it'll say 3 lines. I'll write it down here. And down here I've got something 1, 2, 3, 4, 5 and a half. So I'll say 5 lines. So that says the strength of the electric field, or the strength that the force would exert on any particle placed closer to the center, would have a stronger force. And the electric field lines are closer together. So the closer electric field lines are, the stronger the electric field is. Now what we're going to do is we're going to look at what happens if we were to place a second charged particle into our situation. So we know that our test point, our little dot that we would have, would be a slightly positive charge. So if I were to place it right in the middle, the slightly positive would want to be repelled by the left positive, and it would be attracted to the negative blue. So in this direction, my field line would want to go away, we want to go towards, right? We want to go away from the positive and towards the negative. And we draw an arrow to show which way it's going. But what if I were to place that particle slightly higher? Something like right here. What would happen with it? Well, we do know it wants to go away from the positive, and it wants to go towards the negative, and directly towards it. We have a vector from the electric field at this positive, we have a vector from the electric field from this negative. And if we combine them, and I were to place a bunch of dots on here, what we would see is we would see the path of the electric field actually show up something like this. As I'm closer to my positive charge, it wants to move directly away from the positive. So it's going to be a very, very strong electric field. So all of these initially should look like they're coming straight out. All of these are going straight away. And same thing with this negative. If I were to place any particle near it, it would want to go towards. Right? So we'd have a bunch of arrows pointing towards it. But as I start to move farther away, it gets less and less repulsion and more attraction from the blue negative. So my lines actually start to show up something like that. And at the very end, I should have a direct line going straight in and a direct line with a straight repulsion. Hang on, Mr. G. I thought you said that all of these lines were supposed to be straight. When we had our last diagram, every single line went straight away. But now all of these lines, except for 1, 2, and 3, are curved. That doesn't make sense to me. And I completely agree with that statement. Yes, that's true. But if we looked at the direct line coming out of each of these, so if I were to draw all of my positives in the green marker, and then I drew all of my negatives in the blue marker, And now what I'm going to do is I'm going to erase all of my black lines. Now, I know this looks a bit confusing, but what I did was I erased all the black lines, I put in some extra blue and green lines, and what we can do is we can examine these. Going back to the black marker, if I looked at where these lines intersected, something like right here, well, I've got a slightly down and to the right, and I've got a slightly up and to the right. Well, the down part from the positive and the up part from the negative would kind of cancel out. They would show that they're not fully helping each other out. That it's constructive, destructive. But they are both acting in the right-hand direction. So if I were to draw the arrow on here, it'd be both of them pointing to the right. And that's kind of what we drew initially. This arrow would show up, and the arc would be about horizontal in the middle. And same thing here. This is going about the same down as this one is going up based off of angles. So right about here, these should both be horizontal. But as I get farther away from the positive, we're still going to look down the bottom. As I get something like here, it's a strong upwards pull and a very, very slight to the right push. Right? So from this point right here, the blue is pulling up a lot. The green, since it's far away, doesn't have much effect on it. So there is slight right, a very, very slight right, but a lot of it is going up. So it should kind of look a slight right, a slight right, but mostly up. And we can do that same thing along the top. Right? At this point, I have a lot, because it's very close to this blue, and it's very close to the negative as opposed to the green positive, that this vector is going to be having a larger effect than the green vector. So looking at it, I should have a strong downwards pull, but both of them are going to the right. So it should do a little something that looks like that. And we can do this with all the points on here, but this shows that each field line is only towards the negative and only away from the positive. But when we look at field lines, we look at what the net is, what the sum of all of these vectors are. The electric field from the positive as well as the electric field from the negative, and we look at them together. So we're going to look at what happens when we put two negative particles into a system. And we look to see what the electric field lines are in this scenario. So we know if we look at the outside of both of these, from the outside, if I were to put a point here, it's going to be attracted, right? My slightly positive particle is going to be attracted to the large negative on this side, as well as it's the same for the other. Right? We can draw that basically every single time. But what about in the middle? Because in the middle, yeah, it should go right in. True? It should go into the middle. But what about a spot right here? What if I were to put my slightly positive point right in the center? What would be the electric field there? Well, if it's right in the center, the pull from this negative and the pull from that negative would be the exact same. So those vectors, my vector showing this direction as well as my vector showing that direction, would completely cancel out. So, in this region, right in the very center, we shouldn't see a single line, should we? But how does that work? Because I have my arrows, all of them pointing in. And if I were to backtrack these, they'd have to meet up, right? But again, it's vector addition. And a positive 2 and a negative 2, when we add them up as vectors, cancel out to be 0. But what if I start to move off to the side a little bit? Let's say I move side as being up, down. So what if I were to put a point here? Well, at this point, it's got a very strong pull towards this negative. It's got a very strong pull towards that negative, right? But the left and the right should basically cancel out. And it should, the resultant vector at this spot should basically be straight down. And if I put any of them near that same spot, they should all kind of be pointing straight down. Maybe slightly off, pointed to the side once I get past the center. And that same thing would show down at the very bottom. If it was right in the center, I should kind of see going directly up. And as I move off to the side, they might be off to a side, they might be slightly pointed to an angle. And as I get closer, if I were to put a point here, it would be a slight pull to the right from this one, a large pull to the left. And both of them are acting up. So I might see something like that. And vice versa over here, I might see something from this point show up as far. And if I continue to look at these lines, again, small arrows for being far away, small vectors, larger vectors as I approach, and as I get really close, it should be a very, very strong field line pointing in. But now let's connect them. So at this point, if I were to continue to trace this line, following it all the way in, we should see a line that kind of looks like that. And as they come down this way, we should see similar things. And as we get closer to the center, we generally will not look at something that is directly in the center. Because if it's directly in the center, it'll bounce back and forth. But we don't look at that. So if it's slightly into one side, we might get something that looks similar to that. And vice versa. The strong pull, both cancel out left and right, left and right, left and right, until I get very, very close, and then it juts off to a side. So we really want to look at the interaction closer to the center. But again, if I were to look at, say, farther away from the center, if I were to look at a point here, look at a point here, we can check to see what that would look like. And they should show up to look something similar to this. Now this is what it would look like if we had slightly more field lines drawn in there. And it shows a region in this area. I'll draw it in green. This green shaded area, especially right in the center, has a very, very, very low electric field. The reason that is because the distance between its next closest electric field line. As we get closer to the center, the net force on here, the net field on here is 0, right? But as I move farther away, it doesn't dissipate very much. It doesn't increase very much, right? The next field lines that I see are pretty far away. So the farther away, the two main things I want you to pick up from this, the farther away electric field lines are in distance. So this distance here, and this distance here, the distance between the field lines, the greater it is, the less the electric field is. The second part is every single time you draw a line, that we look at a line at that particle, no matter what particle it is, which charge it is, the line has got to be perpendicular with your surface. So my surface right here is a sphere. Every line that comes in and out of this has got to be perpendicular. If it is not, it's not showing the correct direction. Because as we get close to an angstrom, 1 times 10 to the negative 15th, if I'm not mistaken, meters away from this particle, it really has no effect from here. It has a very, very large effect from this negative 1. So it'll have to be perpendicular to our spot, to our surface. So far, we have gone through the conceptual ideas. We've been able to look at how field lines enter into and leave charged particles, as well as the interaction between like charges as well as unlike charges, and looking at the electric field lines. Now what we're going to try and do is we're going to put some mathematics to it. And it's very similar to what we did with electrostatics of forces, where we had a charged particle as well as a second charged particle, and we looked to see what the force was between them. But now what we're doing is we are putting a test point in this spot, because electric fields happen no matter whether there is a charge there or not. So based off of our initial equation, where I had the force is equal to Coulomb's constant K multiplied by, we used Q1, Q2, but what we're going to use capital Q for our source, for our big charge, and a lowercase q for our test point charge. And then again, the distance between them squared. It was an exponential decay when we went away. The farther away we were, the force we found out decreased exponentially. Now, what we look at is we need to get rid of this test point, because we're looking at the electric field. We don't care about the force that's happening. So in order for us to remove that point, we're going to divide by lowercase q. So if I divide everything by lowercase q, I should get the force that's exerted divided by the charge of that particle is going to be equal to K, the Coulomb's constant K, multiplied by my source charge, Q, all over R squared, because we're finding it at that same distance. And this would tell me what the value of my electric field is. Similar to going back to gravitational, this would tell me what the acceleration due to gravity is this far away from the center of the Earth, or from the center of a mass. So I've got a diagram for you guys. And what I drew is I have a negatively charged particle and a positively charged particle. Both of them have the same value. And I have a test point, some distance away. We'll just call it distance r. Right? So their value of y down and y up, and a distance of r away. Now, I want you to take a moment. You're going to pause the video, and what I want you to do is I want you to draw on your test point what you think our vector lines should be in terms of electric field, based off of Q2 as well as Q1. So I want my two separate vectors. I'll give you a second to do that. Push pause, and then start it back up when you're ready. Now hopefully what you've drawn is from Q2, which is a positive, and my little test point, which is also positive. We should see a repelling action, right? So my action would go through my test point and away. So I should see something that shows, E2. As well as now, with my negative Q1 and my positive test point, there should be an attraction going towards that upper point. So now I have E1, E2. Not drawn to scale, these two arrows should be the same magnitude. So, now that I have these, what can we say about the horizontal components of these vectors? If I have a positive and I have a negative, what can I say about the sum of my positive, or the sum of my horizontal vectors? Hopefully what you say is that acting in the horizontal direction and acting in the horizontal direction for the top one, they should be exactly opposite. So if I were to draw it out, I should see E2, the horizontal component, and E1, the horizontal component, are the exact same values, but in opposite directions. Which means when I add them together, when I try and find out what my net is, my E total, or my net electric field, which is E1 plus E2 plus E3, any other number of charges that I have, right? So it's a sum of all of them. So if I look in the horizontal direction, the sum of them gives me 0. And then when I look to say the vertical components, I have E1 and E2, both of them acting in the positive direction. So my net force, my net electric field should be in the upwards direction. All right, here's the second part of what I want you to do to pause. You're going to pause the video, and I want you to tell me is how to express E total. We can figure out, we know a certain angle. We would be able to calculate what this certain angle is. But knowing an angle, and going back to our trig functions, sine, cosine, tangent, how can I find out what E total is? So we should have E total is equal to what? Take a moment, pause it, write down what you think it should be in terms of sine, cosine, tangent. Hopefully, what you said was my total. Since my theta goes from my hypotenuse to the adjacent side, I would say E total is going to be E2 cosine theta plus E1 cosine theta. Because both of these are acting on the adjacent angle, on the adjacent side. So my electric field would be the cosine of both of those, added together. So now what we're going to try and do is we're going to try and figure out what our net electric field is at this point. But we're going to work one step at a time. And the first step is trying to find out what the value of each of my vertical components are. So I can say the value of E2 is equal to E1. The reason that is because both of these have the same magnitude of charge. Neither of them vary, so they have the same force being applied, or the same electric field at this location. But what is that equal to? That should be equal to K multiplied by my charge cosine theta all over, all over what? Well, if I'm looking for this distance, it's got to be that distance, my diagonal. How am I going to be able to get a diagonal from here? Well, hopefully, you should say, well, I've got an R, which would be a leg. I've got Y, which is another leg. So I should be able to say my hypotenuse would be A squared plus B squared equals C squared. The square root of R squared plus Y squared. Now, my total electric field at this spot would be the sum of all of these, right? And if we've already said KQ cosine theta over the square root of my two legs squared gives me the value of 1. But I need to find out what both of them are. I should be able to just say, take this value and say my E total is equal to, again, Coulomb's constant K multiplied by a charge of one of the particles times the cosine theta all over the square root of r squared plus y squared. But I have to take that value and multiply it by 2 because I've got both charges. So I have to take that value, multiply by 2.